Okay, the time now is 7 p.m. Good evening. My name is Richard Carr, and thank you for tuning in for this live stream MAE 106 tutorial. I hope everyone is able to hear me talking. Let me just check in the chat. Let me just have a quick listen to see. Nope, I don't know if... Okay, so I'm just going to check to make sure if anyone is hearing me. Okay, so what I'll start to do is just talk a little bit about... Okay. Are you able to hear me? And we'll see. Sorry about the keyboard. The keyboard is mechanical, so... But, okay, what I'll start to do is just kind of talk a little bit about the test that's happening tomorrow. Excellent. Good. So I'll keep going then. So tomorrow's test is going to be on probability theory, and it's covering the assignment 8 that we did, assignment 9, and assignment 10. And tonight, I hope to be able to cover some of the topics again, and to answer any questions that pop up on the chat. If you have questions from the textbook, I have the textbook here, so just give me the exercise number and I'll work it out on paper. So, again, you should know all the definitions and formula, knowing what an experiment is, knowing what a sample point is, a sample space, an event, the union of two events, the intersection of two events, mutually exclusive events, complement, uniform, sample space. And you should be able to do the probability of an event in a uniform sample space. We have some exercises for that as well. So what we can do is pick one of these exercises from, say, section 8.2. So let me just, I can actually pull up one of the exercises. Okay, so 8. Just give me one moment while I look up something in 8.2. Let's do one of these questions. So, let's do one of the questions that are from 8.2. And so this says a game involves rolling a 12-sided die with numbers 1 through 12. The desired outcomes in the game is to roll an even number or a multiple of 3. Are these events mutually exclusive? Okay, so what it's kind of asking in this case is, well, we'll let E be the event that we roll an even number. Okay, and we'll let F be the event and it's a multiple of 3. So our event is, in this one for E, it rolls an even number. Oh, maybe I should write what the sample space is. So that's the sample space S right here. And it's 1, 2, 3, all the way up to 12. And so for E, this is the even number. So it's going to be 2, 4, 6, 8, 10, up to 12. And here is F. F is a multiple of, we have 3, 6, 9, and 12. Now what it's asking is are these events mutually exclusive? And mutually exclusive means that the events have an empty intersection. So we'll check. The intersection between E and F, oops, I had a handshake there, is, well, we check between to see which elements are in common. So I see, actually the only one that I see, oh, there's 6, because it's 6 is there and 6 is there. 9 isn't in here, but we do have 12. So the intersection has the sample points 6 and 12 inside of it. But this is not empty. So it does not equal the empty set. So therefore, E and F are not mutually exclusive. Okay, so we did one of those out of section 8.2. We could do the next one, I guess. So let me just fix that up there. This one is asking, what are all the possible events of the sample space? S is equal to H and T. So this is kind of, that would be like rolling a die. This would be heads and this would be tails. And so what are all the possible events? Well, that means what is the power set of S? What are all the possible subsets that I can create from this? And well, a quick way of doing this would be, well, we could do a tree diagram. So it could be we could ask if it's heads. So in this case, it could be no, or sorry, yes, it's heads, or no, it's not heads. The other one I have is it could be tails, and it could be, yeah, there is tails for the second one. It could be not. Oh, all the possible. Yes. And here we go. So here we go. Down this one, so no heads, no tails, so that would just be the empty set. We could have no heads and a tail, so we'll have, here's a tail. I could have heads and no tail, so that's just heads. And the last one is heads and tails. So there is my all the possible events. So all the possible events of the sample space is the empty set. I could have just tails, just heads, and heads and tails. And I covered up what exercises I have. Let's do a question about conditional probability. Let me just look for one. So let's go into section 8.4. Let's do 8.5. Oops, there we go. Unless somebody else has a question that they want me to specifically work on, I'll just keep working my way through some of these random questions. Let's do. Could you do a Bayes theorem question, please? Okay. So, let me see if I can find one. So I'll try to, oops. So let's do one. So 11. Sorry, this is. Let's do. Okay, we'll start off with this question right here. Okay, so unfortunately that is not showing up very well, so I'll just draw it out again. So this is exercise 8.11.1, and so we're given a probability tree. We have probability of E, we have a probability of F, we have a probability of G, and we're also given H prime. Oh, it was clear. Okay. Okay. So here I get 0.4, I have 0.1, I have 0.6, and I have 0.2 here, and I have 0.3. And so I have some missing probabilities here. So we can start to fill this in. The branches need to sum up to 1. So I have 0.1, I have 0.6 here, so I am up to 0.7, which means then the remaining probability here has to be, so 0.6 plus 0.1, that's 0.7, so that means that I have 0.3 left here. Now for this, for these branches right here, I have a 0.4, and this has to sum up to 1 as well. So the complement of this is 0.6. The next one I have down here is I have 0.2, so this means by the complement, that's 0.8. And the last one right here, this needs to sum up to 1 as well, so this is 0.7. Okay. So we filled in the probabilities for it, and the next question that we have was part B, and it was find, here's I, the probability of H given E. Now, what this is asking us is finding the probability of H given E. But what that question is really asking about is do you know how to read this probability tree? And right here, this is the probability of E. And this probability here is the probability of H occurring given that E has happened. So in fact, this is the probability that H occurs given that E has happened. And conversely, down here, this would be the probability that H prime happens, or H complement happens, given E has happened. So in this case, when we find the probability, it's just, in this case, just reading off just that 0.04. So that is just 0.04. Same thing happens here. I have the probability of H given F. Well, that's me just reading off this probability. So the probability of H given F, that's just 0.2. And probability of H prime happening given G is just 0.3. So that's just reading off of the probability table. Now, 4 is a little bit more tricky because 4 is asking what is the probability of E given H. So what we're trying to do is figure out what the probability of this happening, given that we've seen H. But H occurs not only here, but it also occurs here, and it also occurs here. So with our conditional probability, remember from our conditional probability formula, it's the probability that both of these happen. So E and H happen because H has happened. So the probability of E happening, so E and H divided by, this is the probability that H happened. Okay. Now when we multiply along the branches, this would give us E intersect H, because this is equal to the probability of E multiplied by the probability of H given E. And that's just a rearrangement of our formula here from originally, because if I just write that again, the probability of E given H divided by we get that formula by just bringing this one over to the left-hand side, and that gives us our formula. So we have our formula for here, and also we have the formulas for E intersect H prime, the probability of F and H, the probability of F and H prime. Here's the probability of G intersect H, and the probability of G intersect H prime. So I also have to, so I have branch 1, I have branch 2, branch 3, branch 4, 5, and 6. So in this case, I want to know this is the branch 1 that we want. We want that branch. But because of H happening in 3 separate locations, I also am going to be dividing by all the possibilities of H. So I have branch 1 where H occurs, I have branch 3 where H occurs, and I also have branch 5 where H occurs. So that's just the probability of E intersect H plus the probability of F intersect H plus the probability of G intersect H. And so I can just read off those. So the probability of E and H, so that's just here, that's just 0.1 times 0.4 plus, I need this one as well, so that is 0.6 times 0.2 plus. Then I have the last branch here, which is 0.3 times 0.7. Okay. Okay. So there's 16 and 21, 730, so it gives me 0.37, and that leaves me with 4 over 37. Now, the way that you would interpret this for Bayes' theorem is, well, usually what we see kind of here is H. We can think of this as like a rash or a symptom. Basically, we have things like diseases. So we have disease, and that causes a symptom. We could call it, say, a fever. So there's a fever, that's a symptom. That's being caused by a disease, but this is what we usually see as a symptom. We don't really know what the disease is, because there could be disease A that causes it, or there's disease B, or we also can see disease C. So in this case, we have H. H could be like our fever that we see. And H prime, or H complement, would be that we don't see a fever. Well, we could ask, given that we have H, or a fever, what's the probability that disease E is what's causing it? Well, that's what we can do for the probability. This would be the probability that, given that we have, what's the probability that we have disease E, given that we have a fever, like a symptom H. And we can actually calculate that. If we have all these probabilities, then given that we've seen the symptom, the probability that's causing this disease is 4 over 37. We don't always have to keep using E. We can in fact use other letters. So we can actually calculate, what's the probability that we don't see H? Or sorry, we could calculate the probability that we don't have a fever, that we have H complement. And what's the probability that it's disease G? So we could do the probability of disease G, given that there's no fever. And it's the same idea again. We want the probability of G and H prime, all divided by the probability of H prime. And we can rewrite everything all out again. But really all you need to remember then is, in the top part, this is the part that we want, so that's branch 6 that we want, divided by, we want all the possibilities where H occurs. So we have H occurring there. We also have H occurring right here on branch 4. And we also have it occurring on branch 2. So without even having to write those branches, I can just look at that. So it's just branch 6, which is 0.3 times 0.3 divided by branch 2, in this case would be 0.1 times 0.6 plus 0.6 times 0.8 plus 0.3 times 0.3. Sure hope I'm doing that correctly. If not, I need to slow down. Good. 9 over 63. That can actually simplify because 63 goes into 9s. Does it? 63 goes into 9. Yeah, it should go 7 times. Now here's a common question. This is exercise 8.11.2. It's considered 2 urns. The first contains 2 white and 7 black balls. So, okay, that's something I should write down. So, urn 1. I have 2 white and 7 black. And urn 2. I have 5 white and 6 black. So we flip a fair coin and then draw a ball from the first urn or the second urn, depending on whether the outcome was heads or tails, respectively. Okay. So what that's saying is I pick from this one or this one, depending if I get heads and if I get tails. Which also means they're telling me while I wrote it. We flip a fair coin and then draw it. Well, that's 0.5 and 0.5 here, or 1/2. Okay. What is the conditional probability that the outcome of the toss was heads, given that a white ball was selected? Okay. So we might need to draw this a little better. So I flip. I get this. So here's 1/2 and 1/2. And then, so on this one I would get heads, then I go into urn 1 or urn A or whatever. And I get a white ball, or I can get a black ball. And the probability of me getting a white ball in this would be 2 over 9. And the probability that I have a black ball would be 7/9. If I go into that second urn, Then I have 5 white balls, and the total number of balls in there is 11. And there's 6 black balls here, and that's 11 as well. So what it's asking me is, and of course I should define my events, you know, H is coin flips heads. It's important to label what events you're doing. T is coin flips tails. And W is a white ball is drawn. And B is a black ball is drawn. Okay, so the probability that we want is, what is the conditional probability that the outcome of the toss was heads? So it's heads, given that a white ball was selected, so W. So again, the conditional probability formula is H and W both occurring divided by the probability that W occurs, because that's the given information. We are told it's a white ball. So then the next one is well, I'll label these here. But here, along this branch here, this is the probability of H and W. This is the probability of H and B, black. This is the probability of tails and white. Here's the probability that this is tails and black. Okay, so we have this branch right here. And that's divided by branch 1, because that's one of those cases. And we have the second case right here, which is 3. Okay, so this is just my thinking. You don't have to write that. If you write something like that on the test, it's not mathematically makes sense. This is basically, you have to write it out properly. So here I have, this is branch 1 multiplied by 2/9 divided by, well, it's this branch 1 plus 1/2 multiplied by 5/11. Okay. So what I'm going to do is have to make this a little easier on me. So I see that I have 1/2 and 1/2 and 1/2 here, so I can actually factor that out. So that I'm left with 1. Okay, so I'm just pulling out the 1/2, so I'm left with 2/9 plus 5/11. So that cancels and this cancels. So now I'm just left with 2/9 divided by 2/9 plus 5/11. And well, now what we can do is 2/9, and we have 5/11. So I'm just making sure I do that correctly. Okay. The only thing I can do is multiply this by... Is that correct, what I'm doing? I think... I sure hope I did that correctly. Did anyone else check that? 22 over 67, I'll check it on this 0.3. Yep. Okay. So, does anyone else have other questions? Or do you want me to just keep working through questions on Bayes' theorem? We can do this one. Whatever you think will be most useful tomorrow. Well, we can try this one then. A box contains 3 coins. Coin A is fair, coin B has 2 heads, and coin C has been modified such that the probability of heads appears is 1/3. An experiment consists of selecting a coin at random, tossing it, and observing the side that lands uppermost. Determine the probability that heads appears. Okay. So I have 3 coins. I have coin, oops, I'll move down here. I have coin A, I have coin B, and I have coin C. Now, okay, let's see if I can do this, bro. It says an experiment consists of this is important right here, selecting a coin at random. So it means blindly picking one of these and tossing it. Now random means, in this case, picking a coin at random means that we're going to have equal probability. So the probability that you pick the coin is 1/3 here, 1/3 here, and 1/3 here. So here's coin. Okay. Now with coin A, it's fair. Let's see if we can do this. Coin fair. Okay, so that means that it's going to have heads and tails, and that's going to be equally probable. So 1/2 and 1/2 here. This says coin B has 2 heads, so it's definitely going to be heads with absolute probability, and that it has tails, this is 0. And coin C has been modified such that the probability of heads appears as 1/3. So I have heads, I have tails here, and the probability of it being heads is 1/3, which means the complement of that should be 2/3 for tails. Part A then says determine the probability that heads appears. Okay. The probability that heads appears. So just heads. Well, in this case, it's just asking you what's the probability for this one occurring, or this one occurring, or this one occurring. So I could actually have it occurring with coin A. Here's a heads, there's coin B, this is where heads is, and here's coin C. So so for this part right here, it's 1/3 times 1/2. So this would be if I had picked coin A. And then for coin B, it's 1/3 times 1. So there's coin B. Plus the probability of coin C is 1/3 times 1/3. So for coin A, it's 1/6 plus 1/3 plus 1/9. And now this is relying on what you know from 103. Sorry, let me just have a sip of this. So all these can be... Oh, I can't do with 6. So I'm going to write everything over 12. So 6 times 12. So what gives me 12 is 2. So 1 times 2. 3 times 4 gives me 12. So that's 4. And here's 12. Oh, nope, that didn't work. So now instead... you should use 18 then. Sorry. And 3. So that gives me 3 plus 6 gives me 9. Gives me 11 over 18. And that's in lowest terms because 11 is a prime number. So it's a little bit more than a half that it's likely that we're going to see heads. Then the next part is if the coin was tossed, showed heads, what is the probability that it was the two-headed coin? Okay. The two-headed coin. So this was for A. So I'll just write B over here. Probability if the coin was tossed, showed heads. So this is my conditional probability. So if this happened, then what is that? So what it's asking is what's the probability of the two-headed coin? That is coin B. So what's the probability of B given that it showed heads? And that is equal to the probability of B and H occurring at the same time divided by the probability of heads, which, oh, that's convenient. We've already calculated this. Perfect. So I don't even have to do very much after this. So the probability of B and H occurring, that's just 1/3. And I've already calculated what the probability of heads is, which is 11 over 18. So here we go, 11 over 18, which is equal to 1/3 multiplied by the reciprocal. 3 goes into 18 6 times, so that I'm left with 6 over 11. And that's in lowest terms because 11 is a prime number, so I can't reduce it anymore. Okay. What can I do now? Let's try this one. So we have two questions I think that are kind of useful. Oh, can you please do 8-7B? Okay. There was just a comment. I was just reading that. But since we know, or since we knew that there were 6 possibilities for B, and only 11 possible ways to get heads, could we have just written 6 out of 11 straight out of the gate? Probably. And the reason being is because you have equal probability for each of these. Now, if you didn't have equal probability for that, chances, then you can't really do that anymore. It's because we have that equal probability here on the initial picking of the coin A, B, and C. So, yes, you could have done that, but again, that was only for a very small instance of this because we had equal probabilities for that. Okay, so I was asked to do 8-7.4B. Okay, so give me a second while I scroll to that. Oh, okay, yes. Of course, we picked the one that's spread on 2 pages. Okay. I'm going to write down kind of the first part of that. So this says, given you got 6 lieutenants, you have 5 captains, 2 majors. Okay. This is a good question to ask. Okay, so given that I have 6 lieutenant, 5 captain, 2 major, Okay, so I'm going to start at least with A first, and then I'll do B. So the probability that you form a committee of 6 people containing 2 lieutenants, 2 captains, and 2 majors. Okay. So what I need to do is the probability that you form a committee of 6 people. First of all, how many people do I have in total? I have 6 lieutenants, 5 captains, so that's 11 people. So far, 11 plus 2 gives me 13, so there's 13 people in total. Okay, there's 13 people in total, and I'm going to form a committee of 6 people, so that's 13 choose 6. Then for the committees that we do want, we have 6 lieutenants, and from that I'm going to pick 2 of them. The next one is I have 2 captains. Okay, so I'm going to have 5 captains. I'm going to pick 2 of them. Multiplied by, I have 2 majors, and I'm going to pick all of them. So there's your probability. And we can calculate that all out. So 6 choose 2. That's 6 factorial divided by 2 factorial, 4 factorial. So I get 6 times 5 times 4 divided by 2 factorial, which is actually just 2, multiplied by 4 factorial. So that cancels. So I'm left with 30 over 2, which gives me 15. So there's 15 right here. 5 choose 2. That's 5 factorial divided by 2 factorial. 3 factorial. So that's equal to 5 times 4 times 3. 3 factorial divided by, so I'm left with 5 times 4 divided by 2. So that's 20, but this can go in twice, so I'm left with 10. So here's 10. And 2 choose 2. There's only one way to do that. 13 choose 6. Okay, and then I have 13 minus 6, which, oh shoot. Well, this is probably the hardest part, this one. Okay, 6 goes into 12 twice, 5 goes into 10 twice, the 2 cancels there, 3 goes into 9 thrice, and what can I do with this 4? Two times 3 is 6. No, that doesn't give me anything. So I'll just rewrite this out. 3 times 2 times 11 times, oh, I had the 8 still left. 3 times, so that 4 goes into 8 twice. Two times 3 is 6. Times 2 is 12. Okay. 13 times 12. $156. And then 156, well, that's easy with the 11 times tables. So again, that just splits again, so that I'm just left with 160. There we go. And I'll check it on the calculator to make sure I didn't do... Yeah, that's right. Okay, so I'm just left with... Okay, so there's that probability. And I think you could simplify that. Yeah. Okay, so we wanted to do B. Probability that you form a committee of 3 people containing 1 major as president, 1 captain as vice president, and 1 lieutenant as secretary. Okay, so I'm going to think about this. So I have a president, I have a secretary, and then I have a secretary, yeah, S. If I didn't have any restrictions on this, then I would have 13 choices for president. Then I would have 12 choices for VP, and then I would have 11 choices for secretary. This is all the possible ways. Because I have 13 people in total, I have 13, 12, 11. Okay. So the probability that you form a committee of 3 people containing 1 major as president. So the major has to be president. So instead, this says that the president has to be a major. And how many majors do I have? Well, I have 2 choices for major. Then for the vice president, well, it has to be a captain. Well, I have 5 choices for captain. And 1 lieutenant as secretary. So I have 6 choices for that. So that's my probability right there is 2 times 5 times 6. So that's equal to 10 times 6 over 13 times 12 times 11. So that's 60. Divided by 13, 12, 11. Again, that was the original number that we had from our previous, which was 1,716. So that's the probability. I have to ask if it's the answer at the back of the book because I don't have, my arm isn't, I can't reach the book from here. I have it on digital, but if I start scrolling through it right now. Hooray, I did it. Okay, that's good. so who has the next question that they want to ask me? So you can ask me questions from the assignments or whatever you like. I almost feel like I need to be a proper YouTuber and say, oh, this has been sponsored by Waterman ink. It is the best ink that you can get for your money. One of the few that make a proper ink still. Okay, well, we can talk about, again, we talked about in class, independence can be a strong assumption. We read through the Sally Clark case. This was about the poor woman who was convicted and had her conviction overturned about that she had potentially murdered her 2 children. So we talked about how an expert witness had testified and made the assumption that independence of 2 events and gave a misleading probability in court. We can also talk about the difference between independent events and mutually exclusive events. Can you use a diagram to illustrate this? Of course. And wow. Basically, the 2 formulas or key things to remember is that if you have 2 events, if the intersection is empty, that's mutually exclusive events. And the probability, I should keep using the same. The probability of the intersection has to be E multiplied by F, the probability of F. This is an independent. So if E and F are independent, then now notice how I did this. I had E and F is equal to the empty set. You can also say that what's the probability of that occurring? That's equal to 0. And just to highlight, there is a difference between this. So I have, this is the empty set. This is what we've been using for our notation for the empty set. And this is 0. So the event E and F is empty is not the same thing as when I start to talk about the probability of that. That has to equal 0. So probability is always a number, and when we start to talk about events like this as a set, then itself has to also be a set. It can't be a number. Okay. I think also in class I mentioned we were talking about a probability square, and I said, okay, well, we could represent probability as an area. And I said, okay, we'll work with probability because probability we can view it as an area. And I said for mutually exclusive events, so here's like E1 and let's say here's E2, there's no overlap between them. So the intersection is empty. Now, how do I show this? How do I show independence? Well, if I put one event here, so because here's length 1 and this would be the probability of E, and if I put another event perpendicular to it, I have F. So here's the length 1, and let's say this is the probability of F. So the area of that would be 1 times probability of E, so that gives me the probability E right here. And right here I have the probability of F, because it's 1 times the probability of F here. So this right here is E intersect F. And along that corner right here, I have the probability of F, and I have the probability of E. And how do I calculate this probability then? Because I've laid them perpendicular to one another, that these are independent events. Because these are independent events, then I can write this as the probability of E and F. I can calculate that. It's just the probability along its sides. So one way of thinking about this is that for independent events, I can lay them perpendicular. And in these ones, the mutually exclusive, these are parallel with no overlap. Okay. Let's do an independence question. Independence is quite a long section. Okay, there we go. Here's a good question right here. Let's turn on my So, are the events E and F independent given the following? This is the probability of E. Let's do this. Move my paper down a bit. So I have A. Well, to check if they're independent, so again, if E and F are independent, then the intersection has to equal the probability of E multiplied by the probability of F. So if this, then that. So let's multiply those two together. So I have the probability of E times the probability of F. And that's equal to 0.6 times 0.3. Okay, and that equals 0.18, which equals the intersection that we were given. So, yes, E and F are independent. Okay, for B, I have E is 0.2. So what I'll do is just 0.2 times 0.3. That equals 0.06. And that's not equal to 0.05, which is the probability of the intersection. So no, E and F aren't. Not independent. And C. 0.7. Oh, well, it looks like we're going to have to do a little bit of work here. So, we have to recall our addition formula. So here's the probability of E plus the probability of F minus the probability of E intersect F. So we're told that the probability is 0.76 for the union. We are told that we have 0.7 for E. We're told 0.2 minus the probability of E intersect F. So just bringing this over to the left-hand side here, I have 0.7 plus 0.2 minus 0.76, which equals, I have 0.9, so I have 0.9 minus 0.76, so that gives me 0.14. Okay, so that's the intersection. And if they were independent, then I could multiply the two together. So do 0.7 times 0.2, which then gives me 0.14. Good, which matches the same thing that I got up there. So yes, E and F are independent. There. Okay, so I had a question that was asking about, can I do 8.915? Oh, that one can be tricky. Let me think about this one. Let me put it on screen. Suppose I wrote down a number between 1 and 10 inclusively, and you wrote down a number between 1 and 10 inclusively. What is the chance that my number is higher than yours? That one is from, I think that was Richard Sullivan's problem that I remember. But, yeah, let me think about this. So we have, I'm also going to go look at my solutions just to make sure that I'm not going to give you the wrong answer. That one's tricky. Yeah. Okay. Suppose I wrote down a number between 1 and 10. So, again, my number is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means inclusively. The probability of me picking any of those numbers should be 1 in 10. So that's my probability. And if I do this independently of you, because I'm trying to keep this a secret, you should also be picking this randomly as well with 1/10 probability. So the probability that you pick the same number I did is 1/10. And the probability that they're not the same number is 9/10. If the two numbers selected are different, then the probability is 1/2 that my number is higher than yours. And it's simply because of this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Because if I picked randomly, it means that if I picked randomly, it means that, you know, on half of them are going to be lower here, and then the half is going to be up there. So what it's asking is then, it's asking what is the probability again, the problem that we face here is we kind of have two cases. I'm just trying to think of this. Really, I have two cases. One case is if we pick different numbers. And the other case I can think of is that the numbers are the same. Different numbers, you have the same numbers. In this case, the probability that you pick the same number as I did be 1/10 over 1/10, which would be 1 in 100. The probability that we picked both different numbers, that's 9 over 10 times 9/10. (81 over 100), no. I haven't picked, so there's got to be cases that I'm missing. So at this point, I have to go with Sullivan's answer, which was the probability that me and you picking different numbers would be 9/10. And the probability that is higher than mine or not, well, we have to pick that they're different numbers. And that my number is greater than yours. Well, the probability that we pick both numbers differently would be 9/10. Multiplied by my number is either bigger or smaller than yours. So it would be 1/2. So 9/20. I'm not particularly fond of that question. It left me very unsatisfied with the way that I explained it. Now, let's do a question that's a little bit more, one I kind of like more, which was the 4 ants that are sitting on the corners of a square. Shouldn't there be a different probability for each number? I'm not quite sure what you mean there. Shouldn't there be a different probability for each number? No. If I pick the number equally likely, my number should be 1/10. And if Josh picked a number, it's 1/10 as well. So the probability that we didn't pick the same number is about 9/10. But let's do this one. Can you do a series on software? Software. No. That sounds incredibly boring. This is much more fun because we get to talk about ants. 4 ants are sitting on the corners of a square. From where it is sitting, each ant will randomly pick an edge of the square and travel along that edge. What is the probability that none of the ants collide? Okay. Ooh, with the power of software. So the probability that this ant will go this way is equally likely, and the probability that this ant will go this way. So we got, it's going to be 1/2 here. So it'll either go right or left. And the same thing for this ant right here. It'll go left or right with 1/2 probability. left or right with one probability, and right or left with one probability. Okay. So in order for none of the ants to collide, they either all have to go in the same direction, clockwise, or alternatively, they have to all go counterclockwise. Okay, so the probability of that occurring is that I need to make sure that this ant is going to go the same direction, so that's 1/2 probability. And each of these ants are acting independently. That's an important assumption. So this ant will go clockwise. This ant will go clockwise with 1/2 probability. This ant here will go clockwise with 1/2 probability. And this one will go clockwise with 1/2 probability. So that's equal to 1/2 to the 4th. And same thing happens when it goes counterclockwise. This ant could go to the turn left or counterclockwise with 1/2 probability. The second ant can go the other direction. So again, the probability is for clockwise, them all going clockwise is 2 to the 4th. 2, 4, 8, 16. So that means that the probability of no collision is equal to the probability that they all go clockwise, which is 1/16, plus the probability that they all go counterclockwise, which is 1/16, which gives me 2 over 16, which then simplifies to 1 over 8. Oh, that's a good question. Somebody's asking, why is it not 1/16 times 1/16? Ah, that's a good question. Because this is by what we call the sum principle. And we have multiplication principle. So we have a multiplication principle. And basically what that means is for a multiplication principle, it means that I have a choice for one thing. And then, so this is kind of like and. Then I have a choice for a second thing. And then I'll just... Second, while I plugged everything back in. Okay, there. Should be working now. Okay. Yeah, so as I was explaining before, the camera cut out. The multiplication principle. So in this case, I have ands. In this case, this is actually or. And I'm using the sum principle. Because I have this case, the clockwise case, or I have the counterclockwise case. And when I use the sum principle, this all going clockwise doesn't affect this case where it's all going counterclockwise. Can I show us how to do 8, 11, 6? Sure. Let's see if I can. Just one moment while I look for it. I'm just scrolling to it. Okay. Am I doing other courses in the future? I don't know. It depends if I'm still employed. Okay, so this one is interesting. A computer program is attempting to predict whether a message is an email or junk mail, otherwise known as spam. The goal of the program is to filter out spam before it clogs the user's mailbox and wastes limited storage space. Yes. We have table 8.11 gives us the data about the program. What is the probability that the program predicts the message is spam, given that the message is actually spam, and not spam, given that the message is actually a program, an email? Okay, so I'll write this down below here. So I have A. Here's the probability that it's spam. Identified as spam, right? Given that it's actually spam. So this would be if I wanted to use conditional probability. The probability that it's identified as spam and the message is spam, all divided by the probability that the message is spam. Okay. And let's see. So the probability that, okay, so it's identified as spam and the message is spam. So that means that it's got to be spam. This is the true class, which is that it's an actual email or spam. And this is the predicted, which is by the program. So it's got to be spam and spam. So it's this one right here. So it's going to be 0.334. That's our probability. And then the probability that the message is spam is going to be just along here. Just along this one right here. So these are my two ones that are here. Because this is where it's actually spam. This is real spam. And so the probability that it is spam is going to be 0.053 plus 0.334. Okay. And so with that, I add up the two numbers at the bottom, so I'm just going to make sure I don't do that too badly. Okay. And that's something that we wouldn't expect you to do on the test without a calculator, so. But that's approximately 0.86305. Okay. Did you want me to do B? Okay. I'm running out of room here, so I'll use a new page. Okay. Probability. What is the probability the message predicts is not spam? Okay. So here's the probability that it's the message is not spam. Given that okay, what is the probability that the program predicts the message? Okay, so this is the prediction. That the message is not spam. Given that the message is an email. So, given that the message is a real email. Okay. So that would be the prediction is not spam, and the message is not spam, is real email. And that's all divided by the probability that the message is real. So you're told that the message is real. So prediction is not spam. So this is the predicted class. It's not spam, so I'm in this folder right here. And the message is real. So this is the number I think should be 0.573. Okay. And then the probability that the message is real. Well, the true class is right here. So this is uh-oh, did I make a mistake maybe? No, that's spam. Oh, no, because this is it right here. I need to be looking through here. So this is where it's really the email is a message. So the probability is right through here. So there's the probability. So the probability is not spam, and then that one as well. Okay. So that's the probability the message is real, is right through here. So there it is. It's just this row right here. So just finishing that up then. .53 plus 0.04. So in that denominator I get 0.613 and 0.543. I'm going to divide that. So I get approximately 0.93475. So yeah, probably the tricky part of that for that problem is just trying to read and understand that table right there. Okay. I haven't checked the email. Nope. Oops. I hope well, I thought I had my email working there, so hopefully no one else was sending me an email. Or that I didn't miss any. Okay. Nope, no emails, good. So, is there any more questions? Okay, since there's no more questions, I'll start to wrap this up. We've covered all the material that, if you did your assignments, assignment 8, 9, and 10, you've covered your concepts, you've done the questions. There shouldn't be anything that you wouldn't be able to handle on the test tomorrow. So, make sure you read the question, make sure that you're defining your events, and read carefully and take your time. Some of it can be a little tricky, but it should be straightforward. My name is Richard Kohar. You've been listening to the MAE 106 live stream tutorial for Test 3. I wish you the best on tomorrow's exam, and I'm signing off. Good night.